The objective of the n-queen problem is precise. Take a specific number of chess queens, let's call that number n, and place all of them onto a grid with matching n by n dimensions. We start with a blank grid, in this case, a 4x4 chessboard. The core constraint of the puzzle dictates that no two queens can exist in a state where they are capable of attacking one another. A chess queen has the highest mobility of any piece on the board. Its attack vectors extend in straight horizontal lines, straight vertical lines, and along all diagonal paths, spanning the entire length of the grid. Placing multiple queens requires navigating a dense, intersecting web of these attack lines. Every new piece added to the board geometrically increases the hazard for the remaining pieces. Attempting to solve this by randomly testing every combination is computationally taxing. As n increases, the number of possibilities balloons, making a blind search impractical for a computer. We need a systemic architectural approach. To prevent the algorithm from checking every single square on the board, we impose a strict structural limitation from the very first move. Look at how this animation enforces our primary rule. The algorithm will only ever place exactly one queen in each horizontal row. By mathematically enforcing this one queen per row rule, we physically eliminate the possibility of a horizontal row conflict occurring. Because two pieces can never occupy the same horizontal plane by design, the algorithm never has to waste processing power checking for those specific conflicts. This single structural rule heavily reduces the computational burden. It narrows the computer's focus entirely to monitoring columns and diagonals. Before committing to any placement on the board, the algorithm must answer a specific question. Is this exact coordinate safe? To answer it, the computer calls the isSafe function. This partial board visualizes the checks. First, a vector shoots upward, verifying if another queen occupies the column. Next, a second vector checks the upper left diagonal. Finally, a third vector checks the upper right diagonal. Here, it strikes an existing queen, failing the test. This function is strictly binary. A position is recognized as valid only if all three directional checks report a clear path. The isSafe function serves as the algorithm's immune system. It guarantees mathematically that no invalid piece is ever permanently placed on the grid. We can observe the complete execution of this logic step by step on a standard 4x4 grid. First, the algorithm tests coordinate 1, 1, locking the queen in place. In the second row, the first two columns fail due to conflicts. The third column is clear, locking the queen at 2, 3. However, row 3 hits a critical failure as intersecting vectors strike every position. This dead end triggers backtracking. The algorithm retreats to the previous row, deletes the queen at 2, 3, and forces it to 2, 4. It repeats this cycle of testing and retreating until it resets the first row and identifies the valid configuration. Backtracking separates a rigid set of instructions from an adaptable algorithm. It acts as an engine of systematic trial, error, and recovery. This branching map is a state space tree. It represents every single theoretical decision and pathway the computer could take while placing pieces. Without safety checks, this map grows exponentially, generating thousands of invalid board configurations. The algorithm utilizes a concept called pruning. This is the ability to instantly sever a branch the moment a single unsafe position is detected. Pruning cuts off doomed pathways early. The computer refuses to waste processing cycles exploring the children of a parent node that has already failed a safety check. This transforms a mathematically impossible brute force task into a solvable logic puzzle, cutting massive volumes of dead weight out of the search process. This split screen shows how those physical board constraints translate into abstract, repeatable code instructions. The logic relies on an iterative loop. The code systematically tests every column in the current row, one by one, until it identifies a safe square. Once a safe spot is secured, a recursive trigger fires. The function calls itself, cloning the exact same sequence of instructions to tackle the next row down. If that recursive function ultimately returns a false state, the physical consequence is immediate. The code triggers the removal of the current queen. Recursion maps perfectly to this algorithm. Securing a piece in row 2 poses the exact same logical problem as securing a piece in row 1. It operates on a slightly smaller scale. We have to evaluate the ultimate mathematical cost of executing this systematic search. This equation calculates the time complexity. You start with n available choices for the first row, but the number of safe choices steadily decreases for each subsequent row. The result is O of n factorial. Despite aggressive pruning, the worst-case scenario demands massive computational time as the board size scales up. The space complexity, however, tells a different story. The memory requirement is highly efficient, rated at O of n. This diagram shows our memory usage. It caps exactly at n blocks because memory is used exclusively for the recursion stack, the digital breadcrumbs the algorithm leaves to remember where it must backtrack. The algorithm is optimized for memory, but the sheer factorial scale means processing time is always the limiting constraint for massive boards. If a valid arrangement exists within the constraints of the puzzle, systematic backtracking ensures it will be found. The strategy rests on 3 pillars. First, enforcing exactly one piece per row to eliminate conflicts. Second, utilizing strict directional safety checks to prune dead branches off the state space tree early. And third, deploying recursive backtracking to mechanically reverse out of algorithmic dead ends. This precise architecture applies to other major computational challenges, which brings us to our next intellectual hurdle, the graph coloring problem. These algorithms are specific logic structures for navigating high-dimensional constraints and systematically recovering from a state of failure to reach a valid result.